Okay, so we're going to see if this works. Hopefully got the audio fixed and got the camera up here. And I think we're going, got the math person, how to be a math person shirt, do any kind of math, be a person. So we should be able to be good. Doing chapter 13, 13.1, paper review. Here we go. So chapter 13 is about vector functions is what it's about. So we started looking at some vectors. Chapter 12. And so they tell us about some vector functions here in chapter 13.1. A vector valued function or a vector function, and I can zoom in. Of course, I got the camera up. So, oh, I didn't mean for that to happen. What did I do? I don't even know. Can zoom in a little bit, make it a little bit bigger. Just an extension of parametric equations, and we looked at parametric equations of lines in chapter 12. And so they say that you could have a vector function with respect to t, where the x coordinate is a function, the g coordinate is a function, and the h coordinate is a function. You can write that in vector notation like this with the angle brackets, or you can write it with I, J, and K. Your choice. And a lot of times t is the parameter. Sometimes they use s as well. And sometimes when they use t, t can be thought of sort of like time. The domain is the set of all real numbers. The domain is the values that you can put in for t. And so, and the range is the set of vectors. And each value of t gives a specific vector. And t is the independent variable. And they just said that the all real numbers on t. This function gives a bunch of vectors. The terminal point of each vector is a point on the curve. So the vector is pointing at the curve in space. It's not a surface. So we looked at things in chapter 12 and we graphed them like planes, and they were a surface, and the saddle was a surface, and paraboloid, and all of those things were surfaces, but this is going to be instead a space curve. The fact that t has a certain domain gives our vector function an orientation or a direction of travel. And so anyway, so we'll kind of look into that just a little tiny bit and see how things go. Here's one that we're kind of familiar with. I hope that you recognize that if I was to, this is a vector function, it's just a line. And so we did those in chapter 12, and I just want to graph it again just so that you can kind of see. This one's not a curve, it's just a line. And so we can pick any value that we want for t, because t is in our domain, any real number. So we could pick 0, for example, if we liked. And then if we did, we're going to get this vector 3 minus 0 is 3. So we're going to get this vector. I'm going to write it here as a vector 3, 0, and 2. And when we plot this vector from the origin, it goes in the x direction 3, 1, 2, 3. Actually, that's from any point. It goes in the x direction 3, and the y direction 0, and in the z direction 2, 1, 2. I'm going to plot that point right there, and I'm going to draw the vector in here. And so the vector that goes from the origin is pointing at that point right there. And so that point is a point on the line. And so we have this point 3, 0, 2 on our line. Then we can let t be any value that we want. So we could let t be 1 if we liked. That would be convenient. If t was 1, then we would get the vector 3 take away 1, that's the ice maker, and 1, 2 take away 1. And when we plot this point, so down here 2 on the x direction 2, and the y direction 1, and in the z direction 1, and we have this vector from the origin, and it's pointing at that point right there. And so this is giving us the point 2, 1, 1. Because this thing is a line, every point that I get, no matter what value I choose for t, will be on this line, is what it will be. So it'll be on that line, no matter what I choose for t. Even if I choose a really obnoxious value for t, like 0.1, which would be totally okay. I don't know that I would want to plot those kind of things because I'm not very good at my plotting when I get things that are a decimal or fraction, because it gets hard to figure out where it would be. I'm going to go ahead and pick -1. Just for why not? So that would give me the vector 4, -1, 3. And so from the origin here down 4, 1 in the x direction, 4, 1, 2, 3, 4, -1 in the y direction, and up 3, 1, 2, 3. And you can see that, and this is the vector, right? This vector right here. But you can see that we're looking at the points that are the on the head of the vector as our points that are on our line. And I'm going to just go ahead and draw it in here. You can pick another one if you want, and you'll see the same thing. And there's our line right there. So I wanted to look at this video, this animation that they have on space curves. Actually, two things to look at on space curves. So let me see here. Computer screen, don't get dizzy here. And Alt Tab. And so this little baby toy right here, and I hope it's showing on your screen. The yellow is a space curve. And the red is a space curve, and the blue is a space curve. And the little beads are going along space curves, just like they were airplanes flying in the sky. Airplanes, because of the way they can just go anywhere they want, up, down, around, whatever have you, they're kind of like space curves. I also wanted to look at this vector value function. And so this just comes from our textbook, and I'm just going to animate it. This is what they've got for their, this one's not a line. This one is a curve, but they have the x component being 6 minus t and 1.5 raised to the t minus 2 plus 2 times the sine of t minus 2. And the z component is a cosine, and it's pretty gnarly function. I wouldn't want to pick points, but here are the points for t that we're choosing. Right now, it's drawing t as 8. We come over here, here's t as 6, and it's drawn all in between -6 and 8. I'll go ahead and let it animate, and you can see the value for t that's going along here. And so it draws out a space curve. So for every value of t from -8 to 8, in this case, that's what the domain is here, it gives a different value. And the vector there is in black. I didn't notice that it had, we're just looking, the points on our curve are just the head of the vector. I didn't notice it had more than one curve, so that's curve 1. So here's curve 2. And I guess I can drag the figure to rotate it a little bit. Well, maybe I'll just animate it and just see what it looks like. And so that one kind of snakes around there. And let's do curve 3. Why not? You can go and look at these if you like. And you can move this bar yourself if you like at any speed that you want. Well, that one's pretty wild, huh? Or you can push animate and have it draw it. And so what the computer is doing is it's choosing values very small, maybe at increments of 0.1 or something like that, maybe 0.01. And it's just plotting the tip of the vector along there in gray. Plus, I didn't know they had more than one here. That's pretty exciting. My gosh, it's not pretty. And then it's repeating on itself there, it looks like, and going around. Oh, that's joyful, just joyful. Okay, so we did a lovely job on that. Ooh, I don't know how to go back, Kevin. Here, and person view, there I am, paper view. Okay, So, I was going to put this as my ordered pair. So you can kind of see that there's an ordered pair and there is a vector, and the vector is pointing at the curve. And that's what this illustration right here, taken right off the internet, is showing. This is the vector pointing to the curve at t is 0. Here is the vector at t is 1. Here is the vector at t is 2. And here's the vector at t is -1, and it creates this curve. And it kind of has direction. That was one of the things they were saying, because the values of t increase. So this is t is -1, t is 0, t is 1, t is 2. So you can see that's the direction of the curve. Anyway, so we did a lovely job on that. And here is a couple for us to try to sketch out ourselves. They're kind of hard to sketch, I have to admit. Oh no. Just a second. Hello, can I call you back? Okay, I'm making a video. Okay. Bye. Sorry, that's my dad, and he's fine. Okay, general sketching strategy. Identify X, Y, and Z. And so we're going to do that. If you can, get rid of T. It kind of helps you a little bit, and use one or more components to get a curve or a surface that the curve will travel along. Then pick values so that you can see kind of how things go. And so we're gonna give a whirl to doing something like that. But like I said, these can be a little bit hard to. They can be a little bit hard to sketch. I found that with a little bit of practice, I was able to identify, though, when someone else had sketched them with the equations, well, which one it had to be. And so, but that took a little bit of practice. And so if I just want to identify what the X component is, the X component is T, and the Y component is T squared, and the Z component is T to the third. This one, they said that T has to start at 0 and is always bigger than 0. So we'll be able to work that out. I can kind of put these together just a little bit if I do, because T right here, and if I put these together with one another, X is T, so that would tell me that Y equals T squared. So I know that every point on my space curve, which is not a surface, it's not, it doesn't have to be a line, but it's some kind of curve, right? Almost my string can make here's my string, can make a space curve, right? Here's my string kind of going circular, or it can go all around. This is a space curve. So it can be out in space. I kind of think of it as an airplane, like where an airplane flies. The space curve is where the airplane flies, around. And particularly like when they fly and they put on like some, I don't know, smoke out the back, and so you can see and they can write. Well, that's kind of like a space curve right there. So we know that every point on the space curve will be on, and I tried to write this as Y equals X squared, replacing T with X, and then didn't quite get it. And that's a parabola is what that is. And in fact, if you let it go along the Z, it's a parabolic cylinder, is what it is. And every single point would be on that. And so if we wanted to draw this in here, we know that every point is going to fall on this parabolic cylinder. And so if I draw that parabolic cylinder in there, it's Y is 0, X is 0. So that's that point right there. And in fact, that's a good point. Do you guys agree? If T equals 0, then my vector, or the head of my vector, an ordered pair, is 0, 0, 0, right? And then if we let T equals, I'm just going to pick my points this way so that you can kind of see that, hey, they're on this parabola. If T is 1, then X is 1 and Y is 1 squared, and 1 here too. I might want to pick a value like half in here. I'm going to erase that one and pick half for T. If T is half, then X is half. y is 1/4, and t to the third, z, is 1/8. If t is 1, they're all 1 here. If t is 2, then we get 2, 4, and 8. If t is, and you'll just notice that when I plot these points, I'm getting this. So here's 0, 0. I'm going to come down here. I'm going to use my little grid, half. So that's half in this direction. In the y direction, trying to make it perpendicular or parallel to the y-axis there. And then it should have been 1/4. So that I did kind of half. So this is here. And then 1/8 is hardly any up at all. I'm going to just put it right there. So that's my point there. So I have 2 points there on that parabola. And these things are going to start lifting higher, right? It's only 1/8 up. This one was 0 up. 1, 1, 1. So down 1. This direction. In the y direction, 1. And in the z direction, 1. So this was kind of my parabola that I kind of have going in here, y equals x squared. It goes straight up, right, and down. And this point has just, it's on that I can't draw it in 3 dimensions, but this is going up and down the z axis. I'm going to try to draw another one in here. And this one's just a little bit, this one is just on the one that's right here is the one that it's on, right? And there's infinitely many of these parabolas. We're going up and down the z-axis, and that's where this one is. It's because it's lifted up onto that. And then 1, 1, 1, we just plotted that one. 2, 2, 2, 4. So down here, 2. And over here, they're kind of hard to see kind of what's going on. They're really something that needs to be graphed by a computer. And so this one is on that one that I have kind of going here. And so this kind of thing is just kind of, it's looping around here, this curve, this space curve, and it's going to go around like that is what it's going to do. But every point is on that, on this parabolic cylinder going up that we have there. So here's another one to look at. I'm sorry, I draw them the best I can. You guys draw them more beautiful than me, which is kind of nice. It's kind of refreshing that you do. And I put a nice drawing of it here. And so I'll just kind of show you that, hey, yeah, those points are going in there. And so how I want to get this surface that holds it, and how I can kind of convince you of that surface that holds this. This is my x, my y, and my z. And I know that, and you guys know too, from the Pythagorean theorem, that sine squared t plus cosine squared t equals 1. That's true. So for us, then, see we're cosine here. This means x squared right here. And this is sine. And so I just used an identity that's always true, and then noticed, oh, wow, look at this. So this is y squared here equals 1. And so that tells me that this thing, x squared plus y squared equals 1, and I'm not looking at z, is a cylinder, right? A circular cylinder. This is a circle. And if z can be anything, z is 1, z is 2, z is 3, then you get a cylinder. And so, so we know that every point on our space curve will be on this cylinder as it goes around. And so we can just pick a few so that we can just kind of see. So like, for example, if we pick t is 0, then we would get, I know that it's a vector pointing to it, but cosine of 0, I have to have my calculator. here to help me out with, like cosine of 0 is 1, and sine of 0 is 0 and 0. So when t is 0, which they said that's the smallest point that we can have for t, we get the first point, which is 1, 0, 0, and that's that point right there. And you notice that it's on the outer, it's on that cylinder. And then we could pick t is pi over 4, say. And then the sine of pi, the cosine of pi over 4 is the square root of 2 over 2, which is around 0.7. And the sine of that is also the square root of 2 over 2. And pi over 4 for t. And that's an ordered pair that would be on there as well. And so this is in the x direction 0.7 and the x direction 0.7-ish, right? And pi over 4, that's 0.75. Pi is 3.14 divided by 4, so about 0.75. So actually almost equidistant at nearly 0.7. So in this direction, 0.7. In the y direction, trying to get parallel, there, 0.7. And then up 0.7 should be right here should be right on that curve-ish. I've got some scaling problems, but well, for one thing, I use this as my 0.7. That was really silly. And because this is 1, so I should flip this over. And this distance right here is 1, so 0.7 is in here. So I should have come down that much there, and then over that much. Parallel, 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 and that much, and then up. And yeah, it's about the same spot. And you could continue on if you said t was equal to, say, pi over 2. The cosine of pi over 2 is 0. The sine of pi over 2 is 1, and pi over 2, which is around 1.57 if you take 3.14 and you divide it by 2. So down this way 0, over this way 1, so that distance of 1, and so over this way 0, down that way 1, and then up pi over 2, and they say that point is right there. There is some scaling issues going there, but and so all of these points are on that cylinder as they go around, and the z values, if you go bigger and bigger to 2 pi, the z values are getting bigger and bigger, so it's lifting it up. And they're really good. See, they can draw it dotted to show that it's behind, and then it comes back around. And so that's what it's doing. It's wrapping around. It's called a helix, is what it is. That'd be really difficult for me to draw, but it's really easy for me to see that, oh yeah, that's what it would be. And so these are things that would be better if you didn't draw them by hand. That one was the worst that's the worst I've done pretty much on my drawing. Okay. Then consider this vector right here. This is on page 4 of our notes. I got it down so that you can see it. And they ask us to find the domain. They're asking us what are the possible values for t. And we said that t could be all real numbers. Well, except for the square root of t. If you have the square root of t, what does that tell you? If t has to be something that you can take the square root of. So I hope you're yelling at your camera, at your phone, whatever you're watching your video on. I hope you're yelling that it has to be greater than 0. So I have that t has to be greater than 0. And then that was for the x coordinate. For the y coordinate, I have that t cannot be 1 because it can't be 0 in the denominator. So I have that t cannot be equal to 1. And then I don't know if you guys remember about the input to natural log. But the input, which is 16 minus t squared, has to be positive. It can't be 0. If you put in your calculator natural log of 0, where's the natural log? Natural log of 0, your calculator will give you error. If you try natural log of a negative, calculator, natural log of a negative, like -8, for example, your calculator will give you error. It has to be positive. So we know right here that from the z coordinate, that 16 minus t squared has to be greater than 0. It can't be equal to 0. It has to be greater than 0. And what we want to do in order to find the domain here is that we want to solve these three, and they're an and in between. It has to meet all three conditions. So it has to be greater than 0 and not equal to 1, and these are the values, and 16 minus t squared has to be greater than 0. And so I like to solve them on a number line, but you do you. You can solve it however you want. And means that it has to meet all three conditions. It can't only meet two of the conditions or meet only one of the conditions, because if it does, then it'll make one of the parts be undefined, is what it'll do. So I'm going to put my number line out here. And oh, I should have had some different colors and did each one in a different color. That would have been snazzy jazzy. And so here we are at, I'm going to put 0 right here. And this says that t has to be greater than or equal to 0. And so I'm going to have here, solid it in here, and all the way going this way. And then the next one says t cannot be equal 1. And so what that's going to be, I'm going to put 1 right here. That's going to create a hole right here in, so this one actually would be, I'll draw all of them and then put them together. And so that you can see all of them, I'll stack them like a Wendy's double stack. So do I have enough room for the Wendy's double stack? So here's 0 going this way. That's the first one. Here's 1, and it would be open, and then it would be all this way and all this way. But remember, we're only interested in the intersection, and that's what we're eventually gonna get. So I'm just graphing each one of them. Now the other one, I don't know if you guys remember how to solve quadratic inequality, but how you do it is you find the boundary. And the boundary happens at equals. That 16 minus t squared equals 0. And so that happens at 16 equals t squared. And that happens when t is equal to plus or minus 4. And so what you do is you put on your number line those values. So here's -4. Some good scale going on here. And over here is +4. And I'm gonna make this one a little bit higher than those. And because this was inequality, strict inequality, I should have open circle right there at -4, and I should have open circle at 4. And it's either in between or it's in the wings. So it either looks like this, from -4 open to 4, like that. It either looks like that, or it looks like this, -4, and then this way, and 4, and then that way. That's how it looks. And I just have to figure out which one it is. And you can easily figure out which one of those two that it's going to be with a test point. So I can test, and I can test anything I wanted. I'm going to test t is 0. So if I do, I get 16 minus 0 squared, and I'm testing in the original inequality, is greater than 0. Well, 16 is greater than 0. That's true. So that means that where 0 is part of the solutions. So that means that it was the in-betweener. And so this is how this looks. And then now we're only looking for values for t, which we have a drawing here of values of t that meet all three conditions. So nothing that's below 0 will meet the first one's condition. If we pick anything over here and we say it's part of the domain, then when we try to do the square root of it, it won't work. And so it has to be, drawing my line here, it has to be this way. Do you guys agree? And we're going to leave out 1, right? So I'm going to start drawing what it looks like. So all three of them are okay right at 0. So this is going to be the answer to all of them. But then the second one, the y coordinate, becomes not okay at 1. So we're going to have to leave out 1. And then all three of them resume being okay, right? The x coordinate, the y coordinate, and the z coordinate resume being okay. They're all okay all the way to 4. These are okay all the way even beyond 4, but this one says, well, at 4 I stop being okay. So we're here at 4, and this goes on over here to 4, and it's an open circle there at 4. Usually you would write your domain in interval notation. It would be much easier than writing it in set notation. So my domain would be 0, and you use a bracket to show include 0, 2, 1, and you use a parenthesis to show does not include 1. And then we would union that with the values that go from 1 to 4 and do not include 1 or 4. So those are our domain of our function here. So we did a lovely job on that. And then the next thing that they do a little bit of limits here. And they say that if you have a vector function with a function in the x coordinate, a function in the y coordinate, and a function in the z coordinate, and if you want to take the limit, then all you have to do is take the limit of each of the pieces. And so all you have to do is take the limit of the components. So here, if I want to find the limit here, I have e to the t minus 1 over t in the x coordinate. Then what I'm going to do is I'm going to find the limit of all three of these. So this is going to be equal to, and I'm going to make my vector notation, the limit as t goes to 0 of e to the t minus 1 over t, comma, and then the limit as t goes to 0 of t over t squared minus 2, and then the limit as t goes to 0 of sine of 2t divided by t. And then I just have to find those limits using proper methods that I learned in both Calc 1 and Calc 2. And so this one right here, can't come from Calc 2 because it's got E in it. We didn't do any with E in Calc 1. And so I noticed that if I was to substitute in t as 0, then I get e to the 0 is 1, and 1 minus 1 is 0 over 0. So this right here is 0 over 0 is what it is if I use substitution. So that means that it's okay to use L'Hopital's rule. So it's okay to use L'Hopital's, and I abbreviate L'Hopital's with an L apostrophe H like that so that people know that I use L'Hopital's. So that would mean then that this is equal to the limit. I got my vector notation there. You take the derivative of that, which is e to the t. Remember, you do the derivative of the numerator divided by the derivative of the denominator. No quotient rule, just the derivative of the top over the derivative of the bottom for L'Hopital's, which is 1. We get t goes to 0. And now e to the 0 is 1. So this is, when we substitute in 1 divided by 1, so this limit is equal to 1. So that's the x coordinate. We want to also do the y coordinate and the z coordinate. So when I stuff in 0 here, in the numerator, I get 0, and in the denominator, I get -2. And when you simplify that, 0 divided by -2 is equal to 0. So no work to be done, 0. And all I had to do is use substitution. Then the last one over there, it has sine in it. And I know that some people would allow you to use, to do L'Hopital's on sine, because this is 0 over 0 if you plug in 0. But you really shouldn't, because you use the limit of sine in finding the derivative of sine. And so it would make it really a circular argument. is what it would make it. So I'm not going to do that. I always call it Theorem 6, even though it's not Theorem 6 in this book. It's Theorem 6 in a book that we used in the past. But that theorem is, I'm going to write it right here, the limit as, and I'm going to not use t, I'm going to use x. Well, that's what they usually use. As x goes to 0, of the sine of x over x equals 1. That's a theorem. I don't know if you guys remember it. I call it Theorem 1. It's from Calc 1. And so what I have to do is I have to match all of those pieces. So instead of x, all of these pieces have to be the same. So I come over here and I look. I have 2t here. I have t here. See, I'm looking here in the denominator. And I have t here. And I can't change the 2t because it's the input into sine. So there's nothing I could do about it. I guess I could write it using the is it the double angle formula? That'd be 2 sine of t over times cosine of t. I guess I could do that. I'm not going to do that, but I'm going to try change all of the rest of them and see if it makes sense to change all the rest of them. So can I change that to a 2t? And the answer is, well, yeah, you definitely could, but what you have to do is you have to multiply by 2 divided by 2. So what this would look like would be the limit as, and then t goes to 0. I'm going to come back on that. So this would be 2 over 2 times sine of 2t over t. And now I'm going to ask you, can I change this instead of being t to 2t? Because they all have to be the same. 2t goes to 0, sine of 2t over 2t, then that equals 1. And the answer is I can, because as t goes to 0, well, what happens to 2t? As t goes to 0, what does 2t go to? Well, 2 times 0 is 0, so 2t also goes to 0, so I can't change that. So now how this looks, and then I'm going to, I wish I would have given myself more room. I guess you guys say that about me behind my back. Some of you say it to my face, but it seems like enough room. And then when I get writing on it, it sometimes it doesn't seem as much room. So this is sine of 2t divided by, and I want to put this 2t here, 2t, and then I'm going to say times 2. And the reason I did that is because I just want to convince you this part right here is the theorem. And that part is going, according to the theorem, to 1. This part's going to 2, right? Right. The limit as 2t goes to 0, this doesn't have a t in it, so that's going to 2. And 1 times 2 is 2. And so if you try to take the limit of this vector, it's going closer and closer to 1, 0, 2 is where it's going. So we did a lovely job on that. I had to use a little L'Hopital's. I had to use a little theorem. I call it Theorem 6. I had to use this theorem right here. And I had one that was just a chug and plug. Then a vector is continuous at A if, and then this is the continuity checklist, if the vector evaluated at A is defined, if the limit as t goes to A of the vector exists, and if they are equal to one another. And so there's 3 things to check. So here they're asking us, hey, is this continuous at t equals 2? So the first thing that we would check, it says use the continuity checklist to justify your answer. So we would check number 1 is the vector evaluated at 2, is it defined? So is this defined? Question mark. So 2 natural log of 2, sure. Natural log of 2, I think, is around 0.7 or something like that. It doesn't matter. We'll say it's good. And then the next one, 1 over t minus 2. If I plug in 2, that would be 1 over 2 minus 2. Is that okay? No, this one is not defined. And so is r at 2 defined? And the answer is no. And so what can we say about continuity? It's not continuous or discontinuous. Oh, so high school continuous at t equals 2. So it's not continuous at t equals 2. So we did a lovely job at that. So these are things that you probably remember seeing in Calc 1. Limits, continuity came right with it because they define continuity in terms of limits. So that's the reason it always kind of comes along. And then page 5. And I don't know if you notice that I have put problem numbers in here, problem number 5 and problem number 6. They're just for my notes. They correspond with anything else, but I thought it might make it more easy to discuss them, and then I didn't discuss them. The following functions are continuous on their domain. Polynomials, rational functions, all of this we knew from Calc 1, root functions, trigonometric functions, exponential functions, logarithmic functions, inverse trig functions, hyperbolic functions. I guess those you learned in Calc 2. The following functions are not always continuous on their domain. Things that are piecewise defined, and step functions. Actually, step functions are piecewise defined, but just kind of as a, I guess, as a good example on those. And then here, the last thing they ask us here to do is they ask us to find a vector function that represents the curve of intersection of the two surfaces. And so anyway, so we're going to give a try to that. Anytime that you have something circular, is that ice cream? Mm-hmm. What kind? What? Oh, what other kind of ice cream do you have? Oh, Lindy's. Oh, after we get done with this, he says, do your video and then you'll get a treat afterward. So anything you have something circular like this, that usually that means that you're going to try the sine and cosine because you have that trig identity here, that sine squared t plus cosine squared t equals 1. And I'll tell you that more often than not, when they're defining the x, they put it with cosine, just FYI. It's not necessary, but if you're wanting to match the back of the book and have something, I mean, there's infinitely many answers for these. And if you're wanting to match the back of the book, well, that's how you can match the back of the book. Now, this time I have equals 4. And so that would mean that it's 4 sine squared t plus 4 cosine squared t equals 4, right? So I'm just kind of building out what I have over here. And like I was telling you that most of the time they let this be your x. So then what we're saying is that if x was equal to, excuse me, this is x squared. Sorry. I wanted that to be my piece there. And then I was like, so I want this piece to have my x. So I'm going to be x squared. So x squared equals 4 cosine of t. So if I say that x squared is equal to 4 cosine of t, would you agree with me that then x is equal to, so take the square root over here, 2, that was a squared. Sorry, that was a squared. It was really a squared. All of the pieces are squared. And so I can unsquare them all. 2 cosine of t, I couldn't mess this problem up anymore. And then also y squared equals 4 sine squared t. So that means that y equals 2 sine of t. And in order to write it as a vector valued function, right, here's my stress level is high. Here's my vector valued function here, right? You need the x coordinate, which I'm now saying is 2 cosine of t. You need the y coordinate, which I'm saying is 2 sine of t. And then now all I have to do is define what z would be. And I see that, oh, well, I have this equation here that has z in it. z equals 1 minus x. Do you guys agree? If I take away x from both sides, we said x was 2 times cosine of t. So this would mean that z equals 1 minus 2 cosine of t. Put that right here, 1 minus 2 cosine of t. And there I have a vector valued function of where those two surfaces intersect one another. This surface right here, which is a plane, and that surface right there, which is a cylinder, right? And where they intersect one another, we have this is what we have. So we did a lovely job on that. Because sine and cosine are periodic, it's just going to repeat itself. And so you could just go 0 to 2 pi, and then otherwise it would just repeat itself over and over again, go round and round. So you could do your domain 0 to 2 pi, and I think you would get the whole picture there. If you have something that's a cylinder and it's intersected by a plane, and that here's my cylinder and it's intersected by that plane, it could almost look elliptical. Okay, so here's another one. We have, I don't know what this shape is. Maybe I should know what that shape is, but, and this one over here, right? And so I kind of have these two things and I want to put them together. And I noticed that they're both equal to z, so I could try that and just see how that worked. So x squared. Sometimes I do something and it doesn't seem to make sense and go to something that would be nice, but I'm going to try this and just see how that works. And so I could square both sides. And if I did, I'd get x squared plus y squared equals 1 plus y quantity squared. So that would be something that would be possible to kind of look at. I could then multiply this out a little bit. So I'm just kind of working on it to see what could make sense, what would be good to assign stuff. So I have right now x squared plus y squared here. So I haven't quite figured it out yet. If I FOIL that out, I get 1 plus 2y plus y squared. And then do you guys notice that the y squareds go away? And now I'm going to have a foothold because now I have one of the variables in terms of the other. So I can easily solve this equation for y. And so this would be x squared minus 1 over 2 equals y. And then I noticed that I didn't expect this to happen, but I noticed then, well, I would also know what z is because it's in terms of y. And so x is the one that's the most complicated. It's over here, right? So what I probably would do because of that, remember there's infinitely many answers here, but x, I would probably let it equal t. Then that would mean that y equals t squared minus 1 over 2. And that would mean that z equals 1 plus y, which would mean that z equals 1 plus, and remember what y was, t squared minus 1 over 2. And, I could put that together with a common denominator if I was so inclined. It wouldn't probably be that hard either. 2 over 2, right, for 1 plus t squared minus 1 over 2. This will make the people at UC Berkeley happy with me because they'll feel like I cleaned this up a little bit here. Negative 1 plus 2. There is t squared plus 1 over 2. So that's what z is. So now I have my vector value function here of the intersection, and it is going to look like t, and then t squared minus 1 over 2, and then t squared plus 1 over 2. And there we have that. Anyway, so that's kind of that story there. Those are the kind of problems that they have in 13.1. And I hope that you do some homework. I hope I put the homework here on the front. page. I'm gonna go look, see if I did. Yeah, give these problems right here a whirl and see how you do on them. And that's it.